Have you ever found yourself, just gazing up at the night sky on one of those rare, really clear nights where the stars, they don't just twinkle, they feel like they ignite the whole vast blackness? It's that moment, isn't it, when you feel utterly tiny, but also somehow profoundly connected to something, well, something unimaginably vast. And you can't help but ask those really big questions. Where did all this come from? What is this universe we're in? Does it have a beginning, an end maybe? That fundamental human curiosity, that deep urge to understand where we came from and where we're going, cosmically speaking. It's exactly what we're diving into today. Welcome back to The Deep Dive. This is the show where we take groundbreaking sources, we sift through them, extract the most crucial bits of knowledge, and, well, package it all up into insightful, maybe surprising nuggets. It's all custom designed to get you up to speed without that feeling of information overload. Today we're embarking on, I'd say, one of our most ambitious journeys yet. We're exploring some truly profound concepts in physics and cosmology, and our main guide for this deep dive, none other than the legendary Stephen Hawking. Specifically, we're drawing on the incredibly accessible yet deeply profound insights from his monumental work, A Brief History of Time. So our mission today is to unpack the very nature of space and time, how our understanding has just radically shifted over the centuries. It's quite a story. We'll delve into the astonishing reality of an expanding universe and its fiery birth. Then we'll shrink right down to the quirky, kind of unpredictable rules of the quantum world, before looking at the fundamental building blocks of reality itself and the four forces that, well, hold everything together. We'll confront the cosmic mysteries of black holes, wrestle with their surprising behavior, and yes, it is surprising. And finally, we'll zoom back out to ponder the universe's grand origin, its ultimate fate, and that seemingly one-way street we call time. And woven through all of this is humanity's enduring, really ambitious quest for a single, unified theory. One theory that ties absolutely everything together. Get ready for some serious aha moments.
Indeed. And what's truly remarkable when you start delving into these topics is their dual nature. On one hand, yeah, they involve abstract mathematical ideas, highly theoretical physics, stuff that feels very remote. But on the other hand, they fundamentally reshape our understanding of ourselves, right? Our place within this grand cosmic tapestry, even the very fabric of existence. Hawking's genius, which is really the foundation for our deep dive today, was his incredible ability to make these complex concepts accessible. He didn't just write for physicists, he invited everyone to ponder the universe's biggest questions. It was like a shared intellectual adventure,
Yeah.
transcending those academic boundaries. So our aim here in this deep dive is to distill the most impactful insights from this really vast and profound source material. We want to ensure you gain a thorough but also efficient understanding of these universe-defining concepts. It's about giving you the essence, really, the core of what you need to know to truly grasp the cosmos around you.
All right, let's kick this off. Let's embark on this journey by first getting a handle on how our view of the cosmos has changed over time. Because before we dive into the really mind-bending physics, stuff that might make your brain do a few backflips, it's really worth appreciating how we even got here, how we arrived at our current pretty astonishing understanding of the universe. For most of human history, our picture of the cosmos was, well, let's just say, a little more self-centered. I mean, if you think about those ancient models, for centuries, the dominant view, championed by philosophical giants like Aristotle, and then later formalized with incredible mathematical detail by Ptolemy, well, it placed Earth right at the center of everything. This was the geocentric model, right? Earth-centered. And honestly, if you just step outside and look up, it feels intuitive, doesn't it? The sun appears to rise and set, the moon goes through its phases, the stars seem to wheel around us every night.
Exactly. It was a model that perfectly fit human perception and also philosophical ideas about humanity's central importance. For a very, very long time, that was just the accepted truth. And that geocentric framework, it was incredibly powerful for its time. It explained a lot of what people could see with the naked eye. But as observations got more precise, especially observing the planets, things started to get complicated. The planets you see sometimes appear to do these strange little loops in the sky. Retrograde motion, they called it. Now, to explain that within an Earth-centered framework, Ptolemy had to introduce these increasingly elaborate systems, circles moving on other circles, known as epicycles.
Wow, circles on circles. Sounds complicated.
It was. It was a testament to human ingenuity, really, trying to make the observations fit the model. But it also hinted, that maybe the underlying model wasn't quite right. Maybe it was fundamentally flawed.
So we had this elegant but increasingly clunky system trying to force what people saw into this preconceived idea. Then came the Copernican revolution. A truly monumental shift, wasn't it? It really kicked off our modern scientific understanding.
This Polish astronomer, Nicholas Copernicus, back in the 16th century, he bravely proposed a really radical idea. What if the sun, not the Earth, was at the center of our local system, the heliocentric model, sun-centered?
And it was an incredibly elegant solution. It explained those perplexing planetary motions much more simply. No need for quite so many epicycles. But as revolutionary as it was, it stayed mostly a theoretical proposal for a while. I mean, it challenged deeply entrenched religious and philosophical beliefs. It wasn't easily accepted.
Right. It needed proof, tangible evidence.
And that's precisely where Galilei comes in. Early 17th century, with the groundbreaking invention of the telescope, Galileo provided that crucial, tangible evidence. The observations that really challenged the old ways and solidified Copernicus's radical vision. His observations were just undeniable. He saw, for instance, that Venus showed phases, just like our moon, that could only be explained if Venus orbited the sun.
Ah, okay. So you wouldn't see all the phases if it orbited Earth.
Exactly. And even more striking, maybe, he discovered 4 moons orbiting Jupiter. Jupiter, not Earth. That was direct proof that not everything revolved around our planet. These findings were, well, seismic. A huge shift, not just in astronomy, but in championing observation, evidence, and new technology as the way to find truth in science. It showed powerfully how new tools could reveal truths our senses alone could never grasp. It completely changed how we approached understanding the cosmos.
So after that earth-shattering realization, literally, along comes Isaac Newton. And Newton, with his concept of universal gravitation, wow, he performed this incredible feat of intellectual unification. It still boggles the mind, really. He basically showed that the force pulling an apple to the ground here on Earth, it's the exact same force that keeps the moon orbiting us and the planets circling the sun. He connected the terrestrial and the celestial, earthly mechanics and heavenly mechanics, with one single elegant law. It was an incredibly powerful, unifying vision. Explained everything from a dropped pen to the majestic dance of the planets. Newton's work was absolutely transformative, no question. He gave us a coherent mathematical framework for understanding the mechanics of the universe, and was spectacularly successful, predicting planetary motions with amazing accuracy. However, despite these huge breakthroughs, Newton himself, and really the prevailing scientific view for centuries after him, still pretty much thought of the universe as, well, static, unchanging, infinite.
With a fixed backdrop. Exactly. An eternal, fixed stage. A grand, immovable setting where all the celestial events played out. Perfectly predictable once you knew his laws. There wasn't really any concept of a cosmic history, a beginning or an end for the universe itself.
So for centuries, the universe was seen as this unchanging, eternal backdrop, like a grand cosmic clockwork just ticking away. But then, early 20th century, something truly astonishing happened. Something that just shattered this comfortable idea of a static universe and set us on a completely different path.
Indeed. And what's truly fascinating here, again, is how observation consistently challenges our deepest assumptions, no matter how intuitive or comforting they might seem. The idea of an unchanging universe held sway for millennia. Then in the 1920s, Edwin Hubble made a discovery that utterly revolutionized everything. Using increasingly powerful telescopes, meticulously observing distant galaxies, he found they weren't just randomly scattered. He discovered that almost all of them, they were moving away from us.
Away, not just randomly.
Away. And not only that, but the farther away a galaxy was, the faster it was receding from us. This relationship, we now call it Hubble's law. And this wasn't just movement through space. This was the profound realization that space itself was expanding, like dots painted on the surface of an inflating balloon. The galaxies were being carried apart by the expansion of space itself.
Wow. Okay, that is a huge leap.
Monumental. It completely shattered the static universe model, and it immediately implied something staggering. If everything is moving apart now, then logically at some point way back in the past, everything must have been much, much closer together, compressed into an incredibly dense state. This insight didn't just tweak a model. It fundamentally shifted humanity's view from a stable, unchanging backdrop to a dynamic, evolving cosmic story, a story we're all part of. It opened the door to the radical idea that the universe has a history, a beginning, and maybe even an end. It changed our cosmic address, our perspective completely. It's really a perfect example of the scientific method in action. Building knowledge layer by layer, correcting old assumptions with new, compelling evidence, even when that evidence forces us to accept incredibly counterintuitive truths.
All right, so Hubble showed us the universe isn't static, it's expanding. That's already a profound shift from what people believed for, well, forever, practically. But what about time and space themselves? Are they just there? Are they absolute, like Newton thought, a fixed stage that everything plays out on,
Yeah.
totally unchanging and independent of whatever's happening within it? Because for Newton, absolute space was this unchanging, fixed, infinite container.
Right.
The universal stage, always there, always the same, no matter what was in it or how things moved.
Precisely. And absolute time was just as universal for him. A single, true clock ticking uniformly for everyone, everywhere, independent of any observer, any event. You could, in principle, synchronize every clock in the universe and they'd all tick away at exactly the same rate, telling the same time forever.
Yeah.
This framework, it made perfect sense within classical mechanics. It was the bedrock for his incredibly successful theories, predicting orbits in motion with stunning accuracy.
It feels right, doesn't it? Our everyday experience seems to support that. But then, here's where it gets truly mind-bending. Along comes a young patent clerk, Albert Einstein. And with a series of just astonishing thought experiments, he completely turns that whole intuitive idea of absolute space and time completely upside down.
And this raises such an important question. What if our intuition, our common sense about space and time, which is honed by our everyday experiences, relatively slow speeds, weak gravity, what if it's just fundamentally flawed when we look at the universe at its extremes, at huge scales or near very massive objects or at incredibly high velocities? Einstein, with his revolutionary theories of relativity, showed us that yes, our common sense intuition can be very, very misleading indeed. In 1905, his theory of special relativity, well, it did something incredible. It unified space and time into a single, inseparable entity. He called it space-time.
Space-time. Not space and time, but one thing.
One thing. 4 dimensions fused together. And he demonstrated that time and space are not absolute and separate. Instead, they are intertwined. They are relative. They depend on the observer's motion, their speed. What does that mean for you? It means your experience of time and even your measurement of lengths and space can literally be different from someone else's if you're moving relative to each other at very high speeds, near the speed of light especially.
So there's no single universal clock.
No single universal clock. Your clock can tick at a different rate than mine. This phenomenon, we call it time dilation. If you were to travel in a spaceship near the speed of light, time for you would genuinely slow down compared to someone back on Earth.
That sounds like science fiction.
It does. But it's experimentally verified. And lengths would also appear to contract in the direction of motion. It challenges our whole notion of an objective universal reality. And then, building on that, Einstein's general relativity, published about a decade later, 1915, took this even further. It didn't just unify space and time, it connected them intimately to gravity.
Oh.
General relativity revealed that gravity isn't some mysterious, invisible force pulling objects together like Newton described. No. Instead, gravity is the warping, the curvature of space-time itself. And that curvature is caused by the presence of mass and energy.
Okay, unpack that a bit. Warping space-time.
Yeah, imagine space-time as like a vast, flexible trampoline. Or maybe a stretched rubber sheet. That's the classic analogy, right?
I've heard that one.
Okay, so if you place a heavy bowling ball on that rubber sheet, what happens? It creates a dip, a curve in the fabric.
It sinks down.
Exactly. Now, if you roll a smaller marble nearby, it doesn't get pulled toward the bowling ball by some invisible string. No, it simply follows the curve in the sheet created by the bowling ball. It rolls into the dip.
Ah, okay, it's following the shape of the space.
Precisely. That's how objects like planets fall towards massive bodies like the sun. They're not being pulled by a force. They're following the contours, the curvature of space-time, which has been warped by the sun's mass. And this elegant framework, this is the essential lens through which we understand the large-scale structure and evolution of the universe, from planetary orbits to the dynamics of entire galaxies. And it laid the theoretical groundwork for predicting really exotic phenomena like black holes and gravitational waves, which we've now detected.
Okay, so Hubble told us the universe is expanding. Einstein gave us these profound new rules for space-time, explaining gravity as the universe's fabric bending and warping. This is already just a massive shift in understanding. But if the universe is expanding now, doesn't that logically imply, well, a starting point? A moment when everything was incredibly close together, packed in tight.
That's exactly right. That's precisely where the Big Bang Theory comes in. It's our leading scientific model for the origin of the entire universe. The core idea is basically that the universe originated from an extremely hot, incredibly dense state. Technically, physicists call it a singularity about 13.8 billion years ago.
A singularity, what exactly is that?
Well, in this context, it's a theoretical point of infinite density and infinite space-time curvature, a point where the laws of physics as we currently understand them just break down. Essentially, the entire observable universe, all the matter and energy we see today, compressed into a space with zero volume.
Wow. Zero volume. Hard to picture.
It is, and crucially, it wasn't an explosion in space like you might picture a bomb going off. It was an expansion of space itself. Space itself began expanding rapidly, carrying all the matter and energy along with it, like raisins in an expanding loaf of bread.
Yeah.
Everything we see today, every galaxy, every star, was compressed into that unimaginably tiny volume. And then, in an instant, it began to expand, and as it expanded, it cooled and eventually evolved into the magnificent, vast cosmos we observe today.
Okay, the Big Bang, our best model. But wasn't there another idea floating around for a while?
Yes, indeed. This is where observational evidence becomes so incredibly powerful, really pushing us towards a scientific consensus. For a time, there was a competing idea, quite popular actually, called the steady-state theory. Proposed mid-20th century, it suggests the universe always looked pretty much the same. Infinite in extent, eternal in duration, no beginning, no end. And as the universe expanded, new matter was continuously being created out of nothing, basically, to fill the gaps and keep the density constant.
That sounds kind of neat, actually. An unchanging universe avoids the tricky question of a beginning.
It did have a certain appeal, a seemingly more comfortable picture, but as I said, the universe had other plans. That alternative just couldn't stand up to the relentless march of evidence.
Right. So what was the killer evidence against steady state and for the Big Bang?
Exactly. The definitive nail in the coffin for steady state and the overwhelming, irrefutable evidence for the Big Bang came from one of the most serendipitous, you could say accidental discoveries in scientific history, the cosmic microwave background radiation, the CMB. In the mid-1960s, two radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Labs with a very sensitive new horn antenna. They were trying to do radio astronomy, but they kept detecting this persistent, faint static, a background noise coming from everywhere in the sky, no matter where they pointed the antenna.
Like interference.
That's what they thought. They tried everything to get rid of it. They checked connections, recalibrated. They even famously cleared out pigeon droppings from inside the antenna, suspecting that might be causing the noise.
Pigeons. Seriously.
Seriously. But the noise remained. Constant, uniform, coming from every direction. It turned out to be something far, far more profound than pigeon interference. This faint glow, this pervasive hum, it is the afterglow, the residual heat left over from the Big Bang itself.
The heat from the beginning of the universe.
Yeah.
Still detectable.
Still detectable. Think of it this way. In its very early infancy, the universe was incredibly hot and dense. A searing, opaque fog of plasma-charged particles, basically. It was so hot that light couldn't travel freely, it just kept scattering off the particles. But as the universe expanded, it cooled down. And about 380,000 years after the Big Bang, it became cool enough for electrons and protons to combine and form neutral hydrogen atoms. At that precise moment, the universe suddenly became transparent to light.
Like the fog clearing.
Exactly like the fog clearing. And the light that was present at that moment was finally free to travel across the cosmos unimpeded. The CMB is that very first light. It's been traveling for nearly 13.8 billion years, stretched out by the expansion of the universe, cooled down until now we observe it as microwave radiation, just a few degrees above absolute zero. This discovery was truly the smoking gun for the Big Bang. It's the universe's baby picture, undeniable proof that there was a fiery genesis, not an eternal, unchanging existence like the steady-state theory proposed.
Wow. So for you, the listener, that's an incredible thought, isn't it? That faint static you might get on an old analog TV, or this ubiquitous microwave background that our satellites map in detail. That is literally the oldest light in the universe, the echo of creation itself. Okay, so we've journeyed from the grand cosmic scale expanding universe, Big Bang, right down to understanding space and time themselves as this dynamic fabric. But what about the really, really small stuff? You know, the atoms, the particles, the fundamental components of everything around us. Turns out when you zoom way, way down to that infinitesimally tiny scale, things get weird, like really profoundly weird. The rules are completely different.
They absolutely are. In the classical world, the world we experience every day, the world Newton described so brilliantly, there's this comforting sense of, well, determinism. If you know the precise position and the precise momentum that's its speed and direction of every particle in a system at a given moment, classical physics tells you can, in principle, predict the future of that system with absolute certainty.
Like a cosmic billiard table. Know the initial shot, know where all the balls will end up.
Exactly. That idea, classical determinism, suggested that if we could just know everything about the universe at one instant, we could know its entire future and its entire past, for that matter.
But quantum mechanics, it throws a wrench in that, doesn't it?
It throws out the entire billiard table analogy. Quantum mechanics, which is the theory that truly governs the world of the very small atoms, electrons, quarks, it replaces that comforting certainty with probabilistic laws. It's all about probabilities, not certainties. And this is precisely where Heisenberg's uncertainty principle comes in. It's absolutely crucial for understanding matter at the atomic and subatomic levels, and it has truly profound implications for our ability to ever fully predict the future.
Okay, the uncertainty principle. I've heard of it. But what's the core idea, simply put?
The core concept is you simply cannot precisely know both the position and the momentum of a particle at the exact same time. It's fundamentally impossible. The more accurately you try to measure one of those properties, say, its exact position, the less accurately you can simultaneously know the other property, its momentum, and vice versa.
And this isn't just because our measuring tools aren't good enough.
No, that's the crucial point. It's not a limitation of our instruments being too crude or clumsy. It's a fundamental inherent property of nature itself.
Yeah.
It's like there's a built-in fuzziness to reality at that level.
That sounds incredibly counterintuitive. Can you give us an analogy, maybe?
Yeah,
Make it a bit clearer?
Sure. Imagine trying to pinpoint a tiny fly's exact location in a dark room while also knowing its exact speed and direction. If you shine a very bright, focused beam of light on it to see exactly where it is right now, the photons, the particles of light themselves hitting the fly, will inevitably give it a little nudge. They'll knock it off course, changing its momentum in an unpredictable way.
Ah, okay. So the act of looking changes what you're looking at.
Precisely. You might get a very clear snapshot of its position, but you've unavoidably altered its trajectory, making its speed and direction uncertain. Conversely, if you tried to measure its momentum very precisely, maybe by tracking its flight path over a period using very low-energy photons that barely disturb it, you'd lose precision about its exact location at any single instant during that path. It's an unavoidable trade-off. The act of measurement itself inherently disturbs the system you're trying to measure at this quantum scale.
Wow. So it's not our fault, it's just how things are down there.
Exactly. It's a fundamental limit imposed by nature, and the implication is profound. Even if we had a perfect theory of everything, a single equation describing all the fundamental laws, quantum uncertainty means we could still never predict everything with 100% precision. We could only ever predict probabilities. What's the probability of finding an electron here or having this momentum? It introduces this inherent fuzziness, this fundamental unpredictability into the very fabric of reality. It challenges our basic intuitions about cause and effect. It means the universe isn't a perfectly predictable clockwork, after all, but more like a dance of probabilities at its deepest level.
That's truly mind-bending. And it doesn't stop there, does it? Things get even stranger in the quantum realm, like the idea of superposition.
Ah, yes, superposition. That's another cornerstone of quantum weirdness. It suggests that a quantum particle, like an electron, can actually exist in multiple states simultaneously. It can be spinning clockwise and counterclockwise at the same time, or it can even be in multiple locations at once.
Multiple places at once.
Until the moment you measure it. The classic analogy is a spinning coin. While it's spinning in the air, before it lands, you could say it's simultaneously heads and tails. Only when it lands, when the measurement happens, does it settle into one definite state, heads or tails. Quantum particles are like that before measurement, a blur of possibilities.
And then there's wave-particle duality too, right? That sounds contradictory.
It does. Wave-particle duality is the idea that things we normally think of as particles, like electrons, can also behave like waves. And things we normally think of as waves, like light, can also behave like particles called photons. So sometimes light acts like a stream of tiny bullets, little packets of energy, that's the particle nature. Other times, it behaves like ripples spreading on a pond, that's the wave nature. And electrons do the same thing. They can act like localized particles, but they can also spread out and interfere like waves.
So which is it? Particle or wave?
It's both. It depends entirely on how you set up your experiment, how you choose to observe them. It's not one or the other. It's this bizarre dual nature that's fundamental to how the universe operates at its most basic level. These properties, uncertainty, superposition, duality, they might defy our everyday logic, but they are absolutely essential for quantum mechanics, which is, despite its weirdness, arguably the most successful scientific theory we've ever developed.
Okay, we've gone from the macro, the expanding universe, down to the micro, where things get fuzzy and decidedly strange with quantum mechanics. But what is all that stuff down there, these tiny fuzzy bits of reality? What are the fundamental building blocks? And maybe just as importantly, what makes them interact? What are the invisible rules, the forces that govern their behavior and make everything from stars to you and me actually exist and hold together?
Right. So starting with the building blocks, we learn in school matter is made of atoms. And atoms, well, they have electrons whizzing around a central nucleus. And that nucleus contains protons and neutrons. Pretty standard stuff so far.
Yeah, basic chemistry.
But then physics goes deeper. It turns out protons and neutrons aren't fundamental either. They're actually made of even smaller particles called quarks.
Quarks. Okay, I've heard of those.
And just to add a layer of, well, intriguing detail, physicists have found that these quarks come in 6 different flavors. Not flavor like taste, obviously, but distinct quantum properties that categorize them. There's the up quark, the down quark, the charm, the strange, the top, and the bottom quark. Each one has its own unique mass and electric charge.
6 flavors. Why so many?
That's a deep question. But these 6 quarks, along with 6 corresponding leptons, the electron is one type of lepton, seem to be the fundamental building blocks of all the ordinary matter we see around us. For instance, a proton is made of 2 up quarks and 1 down quark bound together. A neutron is 1 up and 2 downs.
Okay, so quarks and leptons are the basic matter particles. But you said that's only half the story.
Exactly. Understanding the particles is one thing. The other crucial part is understanding the fundamental rules, the forces that govern how these particles interact, how they talk to each other, if you like. Beyond the particles themselves, there are these forces that mediate all interactions, dictating how everything behaves, from the tiniest subatomic scale to the largest galactic structures. And in our current understanding, a best model, there are 4 fundamental forces of nature.
4 forces. Okay, what are they?
All right. First, there's gravity. This is the one we're all most familiar with, right? It keeps our feet on the ground, makes apples fall, keeps planets orbiting stars. It's actually by far the weakest of the 4 forces at the particle level. But crucially, it has an infinite range. And because everything with mass or energy feels its pull and its effects add up over large distances, it becomes the dominant force on cosmic scales. It shapes galaxies, clusters, the whole universe's structure. And theoretically, gravity is thought to be mediated or carried by a hypothetical particle called the graviton, although we haven't directly detected gravitons yet. That's a major experimental challenge.
Okay, gravity. Weak but long range. Got it. What's next?
Next up is the electromagnetic force. Like gravity, it also has an infinite range, but it is vastly, vastly stronger, unimaginably stronger than gravity at short distances. This force affects only particles that have an electric charge, and it's responsible for, well, almost everything we experience in daily life apart from falling down. It holds atoms together by binding electrons to nuclei. It holds molecules together, dictating all of chemistry, all chemical reactions, and therefore all of biology. It's responsible for light, electricity, magnetism, radio waves, basically all forms of electromagnetic radiation.
So like when I turn on a light or use my phone.
Exactly. That's the electromagnetic force at work. Its force-carrying particle is the photon, the particle of light.
Okay, 2 down. Gravity and electromagnetism, what are the other 2? They sound more exotic.
They operate on a much smaller scale, deep inside the atom's nucleus. So third, we have the weak nuclear force, or sometimes just the weak force. This force is responsible for certain types of radioactive decay. It allows, for instance, a neutron to change into a proton, emitting an electron and another particle called a neutrino. This process is absolutely crucial for nuclear fusion in stars like our sun. It helps power the stars and create heavier elements. Its range is incredibly short, much smaller than the size of a proton, but its implications are huge for stellar evolution and the composition of the universe. Its force carriers are particles called the W and Z bosons, heavy particles.
Right, the weak force, responsible for radioactivity. And the last one.
Finally, number 4, we have the strong nuclear force, or just the strong force. And as the name suggests, it is by far the strongest of the 4 forces, but it also has the shortest range, confined essentially within the nucleus. Its main job is, first, to bind those quarks together inside protons and neutrons. Remember the quarks? The strong force holds them together, mediated by particles called gluons.
Gluons, like glue.
Exactly like glue. And then its other crucial role is to hold the protons and neutrons themselves together within the atomic nucleus. It has to overcome the immense electromagnetic repulsion between all those positively charged protons crammed into that tiny space. Without the strong force, atomic nuclei would just instantly fly apart. Matter as we know it couldn't exist. You and I couldn't exist. It's absolutely essential.
Okay, so quarks, gluons, protons, neutrons, held together by the strong force. Got it.
So those are the 4. Gravity, electromagnetism, weak nuclear force, strong nuclear force, each operating at different scales, different strengths, mediated by different particles. It's like, as you said, 4 different languages describing how things interact.
And the ultimate goal, then, for physicists, is to find one single language, one theory.
Precisely. The dream, the ultimate quest, is to find one elegant, overarching theory, a unified framework where these 4 apparently disparate forces are revealed to be just different aspects, different manifestations of one single underlying fundamental force or principle. It's all about seeking simplicity and elegance at the very deepest level of reality, the theory of everything.
Speaking of gravity, and especially general relativity, more dramatic predictions, let's talk about something truly extreme, something that for decades really did sound like pure science fiction, maybe pulled straight from a cosmic horror story. Black holes. Yet they are very real, aren't they? Astronomers have found compelling evidence for them all over the universe.
Oh, absolutely. They're a confirmed prediction of general relativity. Their formation is pretty spectacular too, though maybe not if you're the star involved. When a really massive star, we're talking typically more than maybe 20 times the mass of our sun, when it reaches the very end of its life, it runs out of nuclear fuel. The fusion in its core stops. Without that outward pressure from fusion pushing against gravity, the star's own immense gravity takes over and causes it to collapse inward catastrophically, just implodes. And if the star's core is massive enough, this collapse doesn't stop. It continues past any known force that could halt it, crushing the matter down theoretically to an infinitely dense point, that singularity again.
Okay, so a dead star collapses. But what makes it black? What's the defining feature?
The defining characteristic is a region of space-time around this collapsed core where the gravitational pull is so incredibly intense that the escape velocity, the speed you'd need to achieve to break free from its gravity, actually exceeds the speed of light.
Faster than light. But nothing can go faster than light.
Exactly. And since nothing in the universe can travel faster than light, according to Einstein's relativity, it means that once anything crosses a certain boundary around that collapsed object, absolutely nothing can escape. Not matter, not radiation, not even light itself. It's trapped forever. A one-way trip.
And that boundary, that's the famous event horizon?
That's the one, the event horizon. Think of it as the point of no return. It's not a physical surface you could, stand on or touch. It's a boundary in space-time defined by gravity. Once you cross the event horizon heading inwards, your future path inevitably leads towards the singularity at the center. There's no turning back. And because light can't escape from inside it, whatever happens inside remains forever hidden from the outside universe. That's why it appears black to us. And for a long time, based purely on general relativity, that's what physicists thought black holes were. Truly black, ultimate cosmic prisons, just consuming everything that fell in, getting bigger and bigger forever, never giving anything back. But then, a truly groundbreaking discovery, again by Stephen Hawking, completely revolutionized this understanding.
Ah, okay. So this is where it gets really fascinating. You're saying Stephen Hawking, in a completely counterintuitive breakthrough, showed that black holes, they aren't entirely black after all. They don't just suck things in forever. That sounds like it defies their own definition.
It certainly seemed to, at first. This was Hawking's incredible contribution. Black holes do emit radiation, very, very faint radiation, but they emit it nonetheless. This phenomenon is now known, fittingly, as Hawking radiation. And the idea came from doing something incredibly difficult but brilliant, combining the principles of general relativity, which describes gravity and black holes on the large scale, with the principles of quantum mechanics, which describes the behavior of particles on the very small scale, right near the event horizon.
Okay, merging the two big theories. How does that make a black hole radiate?
Well, the mechanism, in simplified terms, relies on that inherent weirdness and fuzziness of the quantum world we talked about. According to quantum mechanics, even in seemingly empty space, it's not truly empty. There's this constant fizzing activity where pairs of virtual particles and antiparticles are spontaneously popping into existence.
Virtual particles.
Yeah, they exist for only an incredibly brief moment, borrowing energy from the vacuum based on the uncertainty principle, and then they usually annihilate each other almost instantly, paying back the energy debt. Too quick for us to normally detect. But right near the event horizon of a black hole, something extraordinary can happen. Imagine a virtual particle-antiparticle pair pops into existence right at the edge. It's possible for one particle of the pair to fall into the black hole, crossing the event horizon just before it can annihilate with its partner. The other particle, the one that just managed to avoid falling in, is now stranded. It can't annihilate with its partner, which is now lost inside the black hole. So this escaping particle becomes a real particle, It flies away from the black hole, carrying energy with it.
And where does that energy come from?
It effectively comes from the black hole's own mass energy. The particle that fell in can be thought of as having negative energy relative to the outside universe, so when it falls in, the black hole's total mass decreases slightly to conserve energy. The escaping particle carries away positive energy. So to an outside observer, it looks like the black hole is emitting particles radiating energy very, very slowly.
Meaning black holes aren't permanent, they can shrink.
Exactly. This constant, incredibly slow emission of Hawking radiation means that black holes are not eternal. They are slowly, almost imperceptibly, losing mass and energy over truly immense timescales. Eventually, over timescales far, far longer than the current age of the universe, we're talking trillions upon trillions upon trillions of years, for a solar mass black hole, a black hole can theoretically evaporate completely, just vanish in a final puff of radiation.
That is absolutely astonishing. Black holes can evaporate.
It was a revolutionary concept. It showed that even these ultimate gravitational prisons have a finite lifespan, linking black holes, gravity, quantum mechanics, and thermodynamics in a profound way.
And this incredible idea, black hole evaporation, it led directly to one of the biggest, most perplexing challenges for physicists, didn't it?
Yeah.
A problem that's still hotly debated today. The information paradox.
Ah, yes. The information paradox. This is a really deep puzzle.
So the question is, if something with specific information falls into a black hole, say, a book containing Shakespeare sonnets, which has a unique arrangement of particles, unique quantum state, and then the black hole eventually evaporates away completely via Hawking radiation, what happens to the information that defined that book?
Exactly. Does the information about the specific arrangement of atoms in the book simply disappear from the universe forever when the black hole vanishes?
Because that would be a problem, right?
A huge problem, because a fundamental principle, a bedrock principle of quantum mechanics, is that information in this fundamental quantum sense can never be truly destroyed. It can be scrambled, rearranged, hidden, but the total amount of information should always be conserved. So if black hole evaporation truly destroys information, it seems to violate quantum mechanics. But if the information somehow gets out, how does it escape the event horizon? The Hawking radiation was originally thought to be purely thermal, random, carrying no specific information about what fell in.
So where does the information go? That's the paradox.
That's the paradox. It's one of the most active and contentious areas of research in theoretical physics today, really pushing physicists to understand the interplay between gravity and quantum mechanics at its most fundamental level. Finding a resolution likely requires a full theory of quantum gravity.
And just quickly, are all black holes the same, or are there different kinds?
Good question. We've mostly been talking about stellar mass black holes, the ones formed from the collapse of those individual massive stars. They might have masses a few times to maybe a few tens of times the mass of our sun. But astronomers have also discovered absolutely enormous black holes called supermassive black holes. These monsters are millions, sometimes even billions, of times the mass of our sun.
Billions? Where are they?
We find them lurking right at the centers of almost all large galaxies, including our own Milky Way galaxy. We have one called Sagittarius A star, right at the center of the Milky Way.
How do we even see them if they're black?
We can't see the black hole itself, but we see its effects. We can see stars orbiting incredibly fast around an apparently empty point in space at the galactic center. We can also see intense X-rays and other radiation emitted from material gas and dust that gets superheated as it spirals into the black hole's event horizon, forming what's called an accretion disk. And more recently, an incredibly exciting development has been the detection of gravitational waves ripples in space-time itself generated when two black holes collide and merge. This gives us a completely new way to hear these cosmic collisions and confirm the existence and properties of black holes. It's a whole new era of astronomy.
Okay, we've talked about the dramatic beginning of the universe, the Big Bang, and now we've discussed black holes potentially evaporating over unimaginable timescales. So what about the universe's overall fate? Where is it all heading? Will it just keep expanding forever, getting colder and darker? Or could there be some kind of cosmic endgame, maybe even a reversal and a collapse?
That's the ultimate question about our cosmic destiny, isn't it? Before we get to the possible fates, it's worth briefly mentioning a key refinement to the Big Bang model that helps explain some crucial features of the very early universe. The theory of cosmic inflation.
Inflation, like blowing up a balloon really fast.
Exactly like that, but on a cosmic scale. The inflationary model proposes that in the very first tiny fraction of a second after the Big Bang, and we're talking in unbelievably short time, like 10 to the minus 36 seconds, just an instant, the universe underwent an extremely rapid exponential expansion. It inflated by an enormous factor, stretching out by maybe a factor of 10 to the power of 26 or even much more in less than the blink of an eye. Much, much faster than the more sedate expansion we observe happening today.
Wow. Why do we need that period of super fast expansion? What does it explain?
It elegantly explains a couple of major observations that were puzzling within the standard Big Bang model. First, it explains why the cosmic microwave background radiation, that afterglow of the Big Bang, is so incredibly uniform in temperature across the entire sky. Without inflation, regions of the universe that are now on opposite sides of the sky would never have had time to interact or exchange heat to reach the same temperature. They were too far apart even early on. Inflation solves this by saying they were incredibly close together, smoothed out, before this rapid expansion suddenly flung them vast distances apart.
Ah, okay. It stretched out a smooth patch.
Precisely. And second, inflation explains where the large-scale structures in the universe, galaxies, clusters of galaxies came from. It suggests that tiny, unavoidable quantum fluctuations, those little uncertainties present in the very early universe, got stretched out by this enormous expansion to cosmic sizes. These slightly denser regions then acted as the seeds, gravitationally attracting more matter over billions of years to form all the structures we see today.
So inflation helps smooth things out, but also plants the seeds for galaxies. Clever.
It's a very powerful addition to the Big Bang theory. Now, regarding the ultimate fate, as we touched upon, it really hinges on a delicate balance. The universe's average density of matter and energy compared to a specific value called the critical density. Our understanding of this total density dictates which of three main possible fates awaits us.
Okay, what are the options?
Option 1. If the actual density of a universe is less than the critical density, it means there isn't enough matter and energy, not enough gravitational pull to eventually stop the expansion. In this case, the universe will continue to expand forever. It will keep getting colder, darker, more diffuse. Stars will eventually brain out. Galaxies will drift further apart. This is often called an open universe, and it might lead to a scenario sometimes termed the Big Freeze or the heat death, where the universe becomes a cold, dark, empty void, approaching absolute zero temperature.
Sounds a bit bleak. What's option 2?
Option 2. If the actual density is greater than the critical density, then there is enough gravitational pull to eventually halt the expansion and even reverse it. In this scenario, the expansion would slow down, stop, and then the universe would begin to contract, falling back in on itself. Galaxies would rush back together, temperatures would rise again, ultimately leading to a big crunch. The universe would return to an incredibly hot, dense state, perhaps even collapsing back into a singularity, maybe mirroring its beginning. This is called a closed universe.
Okay, expand forever or collapse back. Is there a middle ground?
There is. Option 3. If the density is exactly equal to the critical density, then the universe is perfectly balanced. It will continue to expand forever, but the rate of expansion will continually decrease over time, getting closer and closer to zero, but never quite reaching it. It avoids collapse, but doesn't run away uncontrollably. This is called a flat universe.
So which one is it? Do we know?
Well, our current observations, especially measurements of the CMB and the discovery that the universe's expansion is actually accelerating, driven by something mysterious we call dark energy, strongly suggests that we are living in a universe that is very, very close to being flat, or possibly slightly open. The odds seem stacked against a big crunch. The most likely fate, based on current evidence, appears to be that endless expansion heading towards the Big Freeze. But, there's still much we don't understand about dark energy and dark matter, which make up most of the universe's density, so the final answer isn't absolutely set in stone.
Right. Always more to learn. Now let's shift gears slightly and talk about something we experience every single second, something so fundamental we barely question it. Time itself. Why does it always seem to move forward? Why do we remember the past but not the future? Why does my coffee cup shatter if I drop it, but the pieces never spontaneously fly back together to form a cup again? This is the deep puzzle of the arrow of time.
It's a profound question, and what makes it particularly intriguing, as Hawking points out, is that most of the fundamental laws of physics themselves don't seem to care about the direction of time. They are largely time-symmetric.
Meaning they work the same forwards or backwards.
Exactly. If you record a video of two billiard balls colliding, obeying Newton's laws, and then you play the video in reverse, it still looks like a perfectly plausible physical event. The underlying equations governing gravity, electromagnetism, the strong and weak forces, they don't inherently distinguish between past and future. Run the equations backwards and they still work. Yet, in our everyday world, and certainly on the grand cosmic scale, time clearly, undeniably, has a preferred direction, a very strong arrow pointing from past to future.
So where does this arrow come from, if not from the fundamental laws themselves?
This is where we often talk about three distinct yet likely interconnected arrows of time, as Hawking discussed. The first, and perhaps the most fundamental one discussed in physics, is the thermodynamic arrow of time. This arrow is dictated by the second law of thermodynamics. This law states that in any isolated system, like the universe as a whole presumably, the total amount of disorder or entropy always tends to increase over time.
Entropy means disorder.
Roughly speaking, yes. More technically, it's a measure of the number of possible microscopic arrangements of particles that correspond to the same macroscopic state. Systems naturally evolve from states with fewer possible arrangements, more ordered, to states with vastly more possible arrangements, more disordered, simply because the disordered states are overwhelmingly more probable. Think of your shattered coffee cup. There's basically only one way for all the atoms to be arranged to form a perfect cup: highly ordered, low entropy. But there are countless ways for them to be arranged as scattered fragments, highly disordered, high entropy. So things naturally go from order to disorder. Broken glasses don't spontaneously reassemble. Heat flows from hot to cold, not the other way around. The universe as a whole started in a very low entropy state, highly ordered, hot, dense at the Big Bang, and is constantly moving towards a state of maximum entropy, maximum disorder, that heat death we mentioned.
Okay, so things tend towards messiness. That's the thermodynamic arrow. What are the others?
The second is the psychological arrow of time. This is our subjective perception, how our minds experience time's flow. We remember the past, but we don't remember the future. We feel time moving forward, carrying us from known past events towards an unknown future. Our brains are structured to process information sequentially. We build up memories from past inputs, creating a sense of continuity and forward progression. This arrow is almost certainly deeply connected to the thermodynamic arrow. The very process of forming a memory in our brain, organizing information, actually increases the overall entropy or disorder of the larger system, our body and its surroundings, by dissipating heat. We create mental order at the expense of greater physical disorder.
Fascinating. Our sense of time is linked to increasing disorder. And the third arrow?
The third is the cosmological arrow of time. This simply points in the direction of the universe's expansion. The universe began expanding from that highly ordered, low-entropy state at the Big Bang, and it's been expanding ever since. So the direction in which the universe is getting bigger is the same direction in which disorder is increasing, and the same direction in which we perceive time to flow. There seems to be a deep interconnection here. The expansion of the universe provides the conditions, the room if you like, for entropy to continually increase. Hawking even explored the really intriguing question: what if the universe were to eventually stop expanding and start contracting in a big crunch? Would the arrow of time reverse? Would entropy start decreasing? Would people start remembering the future and forgetting the past? He argued quite compellingly that it probably wouldn't. Even in a contracting universe, the conditions favoring increasing disorder would likely still dominate, meaning the thermodynamic and psychological arrows would probably keep pointing in the same direction, even as the cosmological arrow reversed.
Wow. So even in a collapsing universe, time might still feel like it's moving forward for anyone inside.
It's a complex theoretical argument, but yes, that's a plausible conclusion. These three arrows, thermodynamic, psychological, cosmological, while distinct concepts, seem to be deeply intertwined, all pointing consistently in the same direction, reinforcing our universal, undeniable experience of time marching relentlessly forward.
Okay, we've seen just incredible progress in our understanding, haven't we? From grasping the Big Bang and the sheer scale of this expanding universe, right down to delving into the tiniest, fuzziest quarks and the forces holding them together. We've journeyed through billions of years of cosmic evolution and explored the infinitesimally small. But the holy grail of physics, the ultimate intellectual quest, it's still out there, isn't it? Beckoning. That single, unified theory that explained absolutely everything. The theory of everything.
That's right. That's the grand challenge, the ultimate dream for many theoretical physicists. And the core of the challenge is this. We currently have two spectacularly successful yet fundamentally incompatible descriptions of the universe. On one side, we have Einstein's general relativity. It's our theory of gravity, describing the universe on the very largest scales, stars, galaxies, the expansion of the cosmos itself. It treats space-time as smooth, continuous, warped by mass and energy, and it works beautifully for macroscopic objects and large structures. On the other side, we have quantum mechanics. This is our theory of the very small atoms, particles, the other three fundamental forces: electromagnetic, weak, strong. Here, everything is probabilistic, discontinuous, quantized into discrete packets. And it works brilliantly in its domain, explaining the subatomic world with incredible precision.
So the problem is these two incredibly successful theories just don't play well together. They speak different languages.
That's a great way to put it. They use fundamentally different mathematical frameworks, different conceptual foundations. General relativity is deterministic, in principle, though chaos theory complicates that, while quantum mechanics is inherently probabilistic. Space-time is smooth in one, quantized and jittery in the other, maybe. And when you try to apply them together in situations where both gravity and quantum effects should be important, like trying to describe the singularity at the heart of a black hole, or the very first instant of the Big Bang when the universe was incredibly dense and hot, the combined equations just break down. They often yield nonsensical results, like probabilities greater than 1, or infinite values for quantities that should be finite.
So it's like trying to use two different maps, one for rows and one for elevation, but they don't line up where they overlap.
Exactly. We need a single, coherent map, a unified framework that seamlessly incorporates both gravity and quantum mechanics, a theory of quantum gravity, and ideally a theory that also unifies gravity with the other three fundamental forces into a single description. That's the ambitious goal of a theory of everything, or TOE.
So where are we on that quest? Are there promising leads?
Oh, yes. This is where we push right to the frontiers of theoretical physics. It's incredibly challenging, requiring new mathematical tools and really out-there ideas. Many brilliant minds are working on it, exploring different avenues. There have been various attempts over the decades. An earlier approach called supergravity tried to extend general relativity by incorporating principles from particle physics, specifically supersymmetry, which posits that every known particle has an unseen superpartner. It showed some promise in unifying forces, but ultimately faced difficulties and didn't provide the complete picture.
Okay, so supergravity was a step, but not the final answer. What's the leading idea now? I always hear about string theory.
String theory is definitely the most prominent and widely researched candidate for a theory of everything over the past few decades. The core idea is truly revolutionary. Quite mind-bending, actually. It proposes that the fundamental constituents of nature, the things we think of as point-like particles, electrons, quarks, photons, etc., are not actually points at all. Instead, they are unimaginably tiny, one-dimensional vibrating filaments or loops called strings.
Like tiny violin strings vibrating.
Exactly like that. Just incredibly, incredibly tiny, far smaller than anything we can currently probe directly, maybe around the Planck length, which is about 10 to the minus 35 meters. Absolutely minuscule. And just like a violin string can vibrate at different frequencies, producing different musical notes, these fundamental strings can vibrate in different patterns, different modes of oscillation. And here's the key idea. These different vibrational patterns correspond to the different types of particles we observe. So one specific vibration pattern might manifest as an electron, another pattern might be a quark, another a photon. And crucially, one particular vibration pattern is predicted to correspond precisely to the graviton, the hypothetical quantum particle that carries the force of gravity.
Wow, so all the different particles are just different notes played on these fundamental strings.
That's the beautiful, elegant idea at its heart. It potentially provides a framework where all particles and forces, including gravity, arise naturally from the behavior of these single underlying objects, the strings. Now, it gets even more fascinating, or maybe weirder, depending on your perspective. For the mathematics of string theory to work consistently, for these strings to be able to vibrate in all the required ways, the theory suggests that the universe might actually need more dimensions than the 4 we directly experience. 3 spatial dimensions plus time.
More dimensions, like hidden dimensions.
Exactly. Most versions of string theory require the existence of perhaps 10 or 11 space-time dimensions in total. The idea is that the extra 6 or 7 spatial dimensions are curled up or compactified into incredibly tiny shapes, curled up so small, again, perhaps at the Planck scale, that we simply don't perceive them in our everyday macroscopic world.
Okay, that is wild. Tiny vibrating strings in hidden dimensions.
It sounds like science fiction, I know, but the mathematics behind it is very sophisticated and elegant. String theory offers this compelling potential framework for unifying gravity with quantum mechanics and the other forces, resolving those infinities that plague simpler approaches. It aims to be that single, coherent description of everything, from the Big Bang to black holes to particle physics. However, it's important to say string theory is still very much a work in progress. It faces significant challenges, particularly in making unique, testable predictions that could be experimentally verified with current or near-future technology. Testing ideas about Planck scale physics and extra dimensions is incredibly difficult.
So the quest continues.
Absolutely. And Stephen Hawking, in his concluding thoughts in A Brief History of Time, reflected on this quest. He pondered whether we would ever actually find such a complete unified theory. And even if we did, would we, as human beings, be capable of fully understanding it? His view, interestingly, was that even if we found this perfect theory of everything, that inherent quantum uncertainty, Heisenberg's principle, would still mean we couldn't predict everything with absolute precision. There would always remain that fundamental probabilistic fuzziness to reality. It suggests that even with the ultimate rulebook for the universe, we might never be able to predict the exact outcome of every cosmic dice roll. Perhaps leaving some room for the unpredictable, for emergence, for complexity that goes beyond simple determinism. Hashtag tag tag outro.
So where does that leave us? We've covered a huge amount of ground today, haven't we? We've journeyed through billions of years of cosmic history, right from that fiery singularity of the Big Bang to the vast, expanding universe we see now. We've shrunk down to the infinitesimally small, the really bizarre, fuzzy quantum realm, where particles play by entirely different rules. We've explored the fundamental particles, the quarks, the leptons that make up everything, and the four fundamental forces that govern how they interact. From the weakest gravity holding galaxies together to the strongest nuclear force binding atomic nuclei. We've peered into the deep mysteries of black holes, discovering, amazingly, they aren't quite so black after all, thanks to Hawking radiation. And we've wrestled with the profound paradoxes they throw up, like what happens to information. We've grappled with that perplexing arrow of time, why does it only seem to fly one way? And we've glimpsed humanity's most ambitious scientific quest. The ongoing search for a single, elegant theory that explains it all. That elusive theory of everything.
It's true. And what's really fascinating, I think, when you delve into these topics is the sheer sense of humility and awe that comes with it. Our best theories, as incredibly powerful and successful as they are in explaining so much of the universe, they are always, ultimately, provisional. They're always subject to being refined or even overturned by new observations, new evidence, new ideas. It's a powerful testament not only to the incredible ingenuity and persistence of the human intellect, striving to understand, but also to the universe's own enduring, seemingly boundless mysteries. There's always more to learn. And Hawking's concluding thoughts in A Brief History of Time really capture this profound implication. He suggested that finding a complete unified theory wouldn't just be the ultimate scientific triumph, it could potentially allow us to address the deepest philosophical questions humanity has ever asked. Why do we and the universe exist? And that ultimate question, why is there something rather than nothing? He famously, and perhaps slightly provocatively, mused that if we were to truly understand such a complete theory, then we would know the mind of God. He wasn't necessarily making a religious statement there, but using it as a powerful metaphor for achieving ultimate comprehension and understanding of the universe so complete that it would reveal its deepest logic, its fundamental workings, maybe even the reason for its very existence.
A truly profound thought to end on. And that brings us appropriately to our final provocative thought for you, the listener, as you reflect on this incredible deep dive we've taken today. If a complete unified theory were indeed discovered, a theory that could, in principle, tell us everything about the universe's mechanics from the very beginning to the very end, would that truly diminish the wonder of existence? Would it turn the magnificent, mysterious cosmos into just a solvable equation? Or would it perhaps open up entirely new, even deeper questions? Questions about consciousness, maybe, about meaning, about the very nature of discovery itself. And given that fundamental quantum uncertainty we talked about, the inherent fuzziness of reality, would some secrets always remain guarded from our grasp, forever leaving an element of surprise and ensuring there's always room for infinite exploration? Something to ponder. We really encourage you to continue your own deep dive into these incredible questions. Maybe pick up Stephen Hawking's A Brief History of Time itself, it's remarkably readable, or explore the many other fantastic resources out there. Thank you so much for joining us on this incredible journey through space, time, and the fundamental nature of reality. We hope this deep dive has provided you with some clarity, some context, and hopefully plenty of those aha moments. Until next time, keep exploring, keep questioning, and keep wondering.